Hi, my name is Kazi, and today I'll be presenting with Juliet about well construction and sustainability. We'll start out by talking about why we drill wells and giving a broad overview. According to the World Health Organization, 844 million people lack even a basic drinking water service worldwide, and that includes 159 million people who are dependent purely on surface water. And that gives a really good illustration of why wells are so necessary. They're a great way to get water to communities that might not otherwise have access to it or have access to a clean source of water. In general, a well works by drilling through the surface into the water table. So the idea there is that deep below the ground underneath our feet, there's water that's accessible if we can drill through the surface using a borehole or a well. And that sits on top of a bed of clay, which prevents it from flowing deeper. And so if we can drill through the surface and access that water, which has been filtered just by trickling through the ground and yet replenished by rainwater, then we can provide a clean drinking water source, even if we're not close to any rivers or lakes or features like that on the surface. Some of the benefits of drilling boreholes are that they don't rely purely on short-term rainfall, unlike catchment systems, and so if one year there's lower than normal or expected rainfall, your community will still have access to water. And since that water has been filtered as it trickles through the ground, this groundwater often doesn't require further purification. Also, there's delayed climate change effects on boreholes, since again, your community won't be getting water immediately from the rainfall that falls. There's a time delay between when the rain falls and when your aquifer gets replenished, but there are also some disadvantages. Drilling a borehole can be much more expensive than catchment. You have to do a hydrogeological survey in advance to make sure that there's water under the ground where you'll be drilling. And even after you've drilled, the flow rate of water might be insufficient to actually support a house or a community or whatever population you're trying to construct a well for. So that's led to the idea of dowsing, the idea that you can detect where water is underground using these rods, and as you walk around, they'll rotate towards the ground once you're over a water source. This method doesn't actually work, but it's still very prevalent in a lot of areas. And so you shouldn't be surprised if you see people walking around with rods or hiring dowsers before they begin drilling.
While wells come with many benefits, we have to think carefully about how to maintain wells for the long term and the negative effects that can be had if care is not taken. One of the most serious side effects of drilling wells without regulation is groundwater depletion. This occurs when water is pulled out of the ground at a faster rate than it can be refilled for a long period of time. And it can have serious damaging effects to the environment, not only including deterioration of water quality for the people who are using the water, but it can also lead to land subsidence, in which the groundwater is no longer existing and the earth above the aquifer falls into the empty space. This has obvious damaging effects, but it doesn't stop there. Reduced waters in streams and nearby lakes can have serious environmental harms in addition to the fact that there's less water to the lakes, because it can harm nearby vegetation and ultimately cause a lot of negative effects in local biomes. In order to avoid groundwater depletion and other effects like it, it's important that community wells take precedence over private wells, and that these community wells are well regulated by an organized body that keeps track of how much water is being pulled out, as well as how much water is re-entering into the aquifer. This is a graph showing just how much groundwater depletion has been an effect of increased use of groundwater. And as you can see, these statistics go from 1960 to 2000. We can only estimate that in the past 18 years that the water demand globally has increased, and so has the danger of groundwater depletion, and therefore the importance of drilling wells sustainably.
So now we're going to start talking about how to drill wells and covering some actual methods of well construction. The first well that we'll talk about is an augured well, and I'll show the video here because it gives a really good description of what's happening. As you can see, there's a bit at the end which is extending into the ground on a long pole, And once it's down there, he starts to spin it, and that actually drills through the soil by hand. This works really well for clay soils because they all stick together and adhere, and then you can lift them back up to the surface and dump them off the drill bit, but it doesn't work as well for loam or sand or silt or other types of soils that will fall off. Less than 125 feet is optimal. That's the deepest distance that the person in the source we were reading from had ever seen a well drilled, but you'll notice that he extended a really long pole down into the well, and as the pole gets longer and longer, it becomes kind of unwieldy to actually spin it and drill deeper. And so if you want to drill a really long distance or really deep, you might need to build a support frame above you to hold the pole as you're drilling. But this method is ideal for year-round water supplies. And as we mentioned, you might need to construct a platform if you're going to be drilling really, really deep. But it's cheap and it balances that out by using more manpower. Another method of construction is a cable to a well. So I'll play a video for this one too, because again, it shows a really good illustration of what's happening. In this case, you don't have to do all of the work by hand because you have a bit connected to what's called a cat head, and that'll drive it up and down for you, so you don't have to do all of the drilling by hand manually. This allows you to drill even deeper wells, potentially up to 200 feet, but it's more expensive since you have some machinery that's doing the work for you, and the trade-off for that is there's less manpower. In general, you might need to erect a tripod over the hole to support the bit as you're drilling up and down, but this is a really good method for a year-round supply of water, and if you don't have the manpower on hand to drill a well by yourself.
So the last kind of method for drilling that we'll cover are rotary wells. Rotary drilling, and I will play the video here, is essentially the most complex of all methods that we're talking about because you just need a lot more machinery in order to be successful. Essentially, the process of rotary drilling involves having a machine that uses an impact hammer to provide energy to the drill bit, push a twisted drill bit into the ground, remove earth from the ground, and essentially reuse that earth, in some cases, to drill deeper into the ground. And there are several types of rotary wells that can be drilled, and we'll go into detail about two of them in the next slide. Air drilling for rotary well drilling is optimal when you're drilling through rock formations, essentially when you're drilling through more difficult surfaces. And what happens is essentially air is used to both cool the drill bit and keep the walls of the borehole intact. This is to ensure that while you're drilling, because rotary drilling is often used to drill deeper wells, that the walls of the well don't fall into the hole that you drilled and essentially cancel out your process. Another important thing that the air is used for is to bring the cuttings to the surface. And this removes the mud and the earth from the hole that you're drilling and essentially speeds up the process. And that's another benefit of rotary drilling, whether it's air or mud, is that it's rather fast and you're able to achieve very deep wells. Mud rotary drilling is good for softer sediments as opposed to air rotary drilling. And it's very interesting because mud, although this is the name of the drill fluid, it's not actually all mud. Essentially what is done, it's able to accomplish similar things as the air drilling or the purpose that air serves in air rotary drilling, but also the mud is collected at the surface, and while the air kind of evaporates after it comes to the surface, the mud is actually reused to drill deeper into the ground. And so that's kind of a broad overview of air versus mud rotary drilling. And there are several other types of rotary drilling that one can use for the process of well drilling also. Here we'll go over some of the different drill bits that are preferred for different materials that you can drill bit through. Roller cone bits are better for harder formations, and they're better suited because they have sharp steel teeth that can go through hard rock easier. Drag bits are made for softer materials, and you can see they have metal faces that allow them to cut more efficiently through softer material like clay, sand, rock. And polycrystalline diamond compact is kind of one of the several types of drill bits that are right in the middle. So it's not ideal for harder formations and it's not ideal for softer formations, but when you have material that's kind of a mix of both, polycrystalline diamond might be your tool. And then reamers are just used to straighten and clean the borehole as you're drilling through, because as previously stated, with rotary drilling, there's more of a chance of the borehole collapsing in on itself, not being drilled straight, just because you're often going to be drilling more quickly and through more surface and just generally deeper into the ground. So to summarize the different well methods that we've talked about so far, we have augured well drilling, and the benefits of augured drilling is that you can drill large diameter wells, and also you need less equipment, and it can be done mostly using human energy, which might be a benefit or a drawback depending on you. However, a serious drawback is that you can only go so far, often to depths of less than 100 feet, and you're limited to softer clay materials. Cable tool wells are one step up from augured wells in that they are more mechanically powered, and the rigs are relatively cheap and easy to maintain, especially when you consider that you're exchanging a lot of power that you would have to do yourself or that a human being would have to do, and translating that into work that can be mechanically done. It's great for difficult terrain in terms of transportation and generally using the cable tool, and you can bail the well whenever you're at a depth that you think is ideal and check how much water is down there, which can be very useful. However, a drawback is that there's a slow rate of well drilling, which can be a serious drawback depending on your project. Rotary wells, as we discussed, are kind of the most advanced, and they provide the quickest wells at the fastest pace, and you can drill quite deep using rotary tools. And similar to cable tool wells, you're able to stop during the process and kind of take a measure of how much water or how much yield that you can get from a given well. But because of all the equipment involved in rotary well drilling, it's extremely expensive, which can be a serious drawback to this method.
So for our last section, we're going to talk about doing good by doing wells and give some design considerations for EWB projects. We'll start by talking about choosing a site. So before you even start drilling, you want to make sure that you have a site plan, which includes things like underground pipes, cables, because you want to avoid drilling into those on accident if at all possible. You also want to think about access roads to the construction site so you can move necessary tools in and all of the material that you're excavating out of the area once you're done. You should do a hydrogeological survey in advance so you know whether there's water where you'll be drilling, and you might want to think about power access if you're doing some form of mechanical drilling, so you know that your driller and potentially an electric pump afterwards will have electricity. You should think about property lines so that the well you're drilling is on public property whenever possible, and you might want to consider future development. For example, if you'll be adding a tank system afterwards to store water that's drawn up from the well, you should make sure to place your well in an area that allows that to happen. A significant thing to keep in mind when choosing a site is to avoid contaminants. If there's a source of waste or animals, such as a latrine or a farm nearby, your well should be at least 30 meters away. If there's a place where organic waste is disposed of, such as a kitchen site, you should be 15 meters away from that as a minimum. And whenever possible, you want to make sure that you're up gradient or uphill of those contaminants so they don't end up trickling down and infecting your water source. There's a lot of different components that go into a well, but here we're going to focus on the non-pump components. So one of the most important things when you're drilling a well is your casing. After you've actually drilled the borehole down into the ground, you can't remove water directly, otherwise all of the soil and dirt from the walls of the well would get into it as you were drawing it up. So you put down something called a casing, which encases your water, and that can be made of PVC or steel, and it's basically just a tube that the water will flow up in. You also need to have a well screen, which is some sort of opening in that PVC pipe or steel tube, which allows the water to get from the ground outside, inside of the tube. However, you don't want mud and dirt and sand getting inside of the tube as well, and so you surround your tube or casing with something called a gravel pack. And lastly, at the surface, you put down something called a grout seal or a surface seal, which helps to prevent runoff from the surface from getting inside your groundwater supply and potentially contaminating it. So when you're doing the surface seal, the thing that you put at the surface to prevent water from running off and infecting your groundwater supply, you want to make sure that it's made of something that's impermeable and inorganic. And so that can be clay, it can be a 1-to-2 ratio of water to cement, it can be chip bentonite, it can be concrete, but it's important to make sure that the depth is at least 5 meters or to the surface of the water table, whichever one is deeper. And that helps to make sure that you don't have contaminants from the surface or the surrounding area infecting your water supply. When you're creating your casing and filter pack, again, the casing is the tube that your water will come up inside, and the filter pack is the gravel or other materials surrounding it to ensure that dirt and mud from the outside don't get inside of the tube. You want to make sure that your casing is either black steel, which is more heat resistant but more expensive, or PVC, which is cheaper. So based on what type of climate you'll be working in and what your budget is, you can choose the appropriate casing. Your filter pack can be a lot of different materials, but regardless of what it is, you want to make sure that it's clean and some sort of rounded material. So that can be sand, it can be gravel, it can be something manufactured, such as glass beads, but you want to make sure that they're rounded so they'll fit together and they're clean. So again, you don't end up contaminating the water that you're bringing up. And whenever possible, you should avoid sand-producing wells. So that's what we call it when sand starts getting inside of your casing and you're bringing that up to the surface along with water. One easy way to avoid that is the sieve test. You might not have the materials to do this while you're out in the field, but if possible, the test works by weighing some material and then placing it on a set of sieves and shaking them for a predetermined amount of time. Then you can take each one of the sieves and weigh them to see what mass of particles are on it and what size sieve it is, so you get a rough idea of what the particle size of the soil that you're working with is. And that can help you determine what casing you want to use, and the size of filter pack material that you need. And lastly, when you're making your well screen, the thing that allows the water to get from the surrounding soil to the inside of your PVC pipe or black steel casing, you need to make sure that it allows the water to enter, but is also compatible with the geologic material, so that dirt and soil from the outside don't get inside. So there's two different common materials that are used for this. You can either have a continuous slot well screen, which is rebar with screen wrapped around it, or the slightly cheaper option, which is slotted plastic pipe. Thank you for watching, and these are our sources if you'd like to look for more information.